Okay, so this is a similar problem to the one that we just did, but I want to have the line integral not equal to 0. So now C is the union of the top half of the circle of radius 1, centered at the origin, so something like this, and then the line segment from 1, 0 to the square root of pi, comma, the square root of pi. So this is going to be something like this. Okay, obviously this is not drawn to scale, and we're going to go in the counterclockwise direction. Okay, and then this here is minus 1, 0. Now we saw in the previous example, or the previous problem, the previous video, whatever, that a potential for the vector field is sine of xy plus y squared. And really, when I say a potential, I don't mean the potential. I do mean a potential, because something like this is also a potential. Because when you take the derivative with respect to any variable, the 1 goes away. This is just the arbitrary constant that always shows up when we do antiderivatives. And again, finding a potential is like a form of finding an antiderivative. We're finding a function we start with a function y cosine xy, x cosine xy plus 2y, and we're finding a function who has that function as its derivative. Remember, the derivative of little f, when the derivative of a real valued function of two variables is a vector field, and so we are finding an antiderivative. Okay, so using the fundamental theorem of line integrals, the thing that we want to compute is f of the endpoint, which is minus 1, 0, minus f of the start point, which is square root of pi, square root of pi. F of minus 1, 0 is sine of 0 plus 0 squared. And f of square root of pi is sine of pi plus pi. And this is just equal to minus pi, because sine of 0 and sine of pi are both equal to 0. Okay, so here's an example where the line integral is not equal to 0. I just wanted to do an example where it wasn't equal to 0, so you didn't think that all line integrals were equal to 0. In the next set of videos, we will see when line integrals are equal to 0.